Welcome, everyone. I'm Dave Roberts, and I'm the head of college. And I don't usually start these off with an apology, but I have to apologise. The reason I'm dressed like this, which folk will realise is not my normal attire, is because I have to rush off to a university event very rapidly. But I was keen to introduce the inaugural, because I think these things are very important. Thanks to Cahur for inviting me to give the introductory welcome. It's the first one, I believe, we've done in college since COVID. Of course, it's a little bit sparse in the lecture theatre for the reasons that you'll understand. But we've got what, 100, and we must be about 100, 125, 130 people.
A bit more than that.
More than that online.
Currently at 170.
Oh wow, 170 online apparently. Many of these are colleagues, but I believe some of them will be family and friends, and your wife and son somewhere hiding away. Oh, there you are, in the audience. So that's great. And also welcome to our guests from the Consulate General of India. That's very nice of you to come. The rest of this, I do have to look up my notes because I want to get it right. So Prashant was born and brought up in Mumbai, in India. He read chemical engineering, worked in Unilever research in Mumbai until 2000, after which he completed his PhD and postdoctoral research at the Department of Chemical Engineering in Imperial College in London. He joined the School of Engineering here at the University of Edinburgh, as a lecturer in 2009, I believe, and was promoted to personal chair in fluid dynamics in 2020, hence the inaugural lecture. He chairs the UK Multiphase Flows and Transport Phenomena Special Interest Group. He's led and participated in several national and international consortia looking at research into phase change fluid dynamics, which I guess we'll get to know a little bit about in the talk. He leads the EEC-funded ThermoSmart Consortium, which is 21 industry academic partners from 15 countries spanning 5 continents for research into phase change thermal management of high-power microprocessors. Anybody who's ever been involved in these European grants will know how complicated it is to keep one of these big programs going. And recently, he was appointed as a member for EPSRC's Engineering Strategy Advisory Team, what we call the SATs, which are very important to us, and they help to shape engineering science research for the UK. So well done getting on those. So all of this stems, I believe, from immersion in science from Prashant's earliest years amongst mathematicians and physicists around India's main nuclear research facility.
Yes.
I believe. So I'm sure we'll benefit this evening from the enthusiasms that blossomed from childhood, and your parents should be proud. Without further ado, let me welcome Prashant. Take it away.
Thank you so much, Dave.
Thank you, Dave. Thank you so much. So thank you everyone for coming to the inaugural. So obviously we are better off, but we want to flow towards a better future. So that's the whole goal of this talk. So before we start anything, I would like to first say a big thank you to the NHS and the health systems worldwide to make sure that we are now able to come here. And of course, there was a lot of contribution from the global fluid dynamics community as well. Essentially, a transmission of the viral particles, you name it, atmospheric effects on that. How does heat and how does actually phase change influence these particles, these droplets which carry the virus and things like that. So there's a lot of work which is actually going on in terms of understanding the spread of this virus. And of course, it'll go on because pandemics don't end. They just keep coming back again and again. So it's important that we know more. And of course, a big thank you to all of our support and essential services. So I think that is very important, without which it would be impossible to have a system where which we are actually able to see each other and speak to each other as well. Okay, so most of you have seen my son. So here he is. He's actually playing with planes. He's completely fascinated by planes. Don't ask me why, but he likes them playing. And so what happened once was I was actually in 2018. I was actually in Japan on a JSPS fellowship. And so he wrote me a letter. And in that letter, he said, how is the weather? He was fascinated by two things, planes and weather. Don't ask me why. If you open my iPhone, and if you see the weather, you will see weather of Antarctica, you will see weather of all the other places other than Edinburgh. But that's him who's doing that. Okay? So obviously, he was fascinated about how the weather is, how Japan is, etc., etc. And then next month, he came to visit me. And when he came to visit me, he was pretty money-minded. He said, give me money, 400 yen and 10,000 yen. For what? To buy the planes. But of course, then, obviously, things, I didn't give him the money, of course. And then we got some planes, though. That's why he has these planes. And then, obviously, the pandemic came, and all of us were making our lecture notes at home. And my son was sitting just next to me because he was also home learning at the same time. So obviously, as I was making lecture notes, he was seeing what I was doing constantly. He used to tell me, oh, Kohora's emailed you. Oh, God. Yeah, it was so funny. So in one of my lecture notes, I have this. You see this? This is basically the island of Madeira off the coast of Portugal. And this is, obviously, these are clouds. And basically, you can see that you've got these clouds about 10,000 feet up in the air, but these are completely influenced by the ground. Okay? And you can see these vortices. These are the one-carbon vortices. So basically, he was completely awestruck by it, And then, as I was preparing for the inaugural, I just asked him, what do you think your dad does? And I said, just draw it and show it to me. So this is what he drew. Where is that thing? Yeah, he drew, of course, his favorite plane. And then he has these flow structures, and you can see these vortices, or close to vortices, whatever is happening. So yeah, so this is what, and he said, this is fluid dynamics by Anag, 10 years old. Okay, which is a fair representation of what fluid dynamics is. So one of the things I would like to mention is, obviously, fluid dynamics, like any other science, has evolved. In the ancient world, it was pretty patchy, but it's not very patchy. It's pretty interesting, actually. So about 42,000 or 35,000 years ago, this is Geisenkloster cave in Germany. So Tim might know this place. And this is the place where they found actually prehistoric flutes. So obviously, people knew how to play with wind or air to make sure that you can create sound. So obviously, they knew some idea about how to really focus sound through air. And obviously, we have the sanitation systems in all these civilizations. Here is the Indus Valley. We also have Sumerian tablets which talk about irrigation work. So people knew how to actually harness the power of fluids. The other thing, obviously, people knew was how to really have naval vessels, so construction of boats. And obviously, you can imagine you've got a boat with several people, so there's a big engineering problem right here to make sure that the boat doesn't sink and it actually goes to the place it has to go. One of the persons who I consider as probably the progenitor of fluid dynamics, modern fluid dynamics, is Archimedes, because that was his principle, which tells that, yes, if something is dense, it will sink, especially on Earth. If something is dense, it will sink. If it is light, it will float. So I would say that he's the father of two-phase flows, or he's the progenitor of modern-day fluid dynamics. And of course, things didn't happen much. I mean, you would get some patchy stuff here and there, but basically, a major amount of stuff happens. Oh, why is it running? Yeah. So major amount of stuff happened during the 17th and the 21st century, starting from, of course, our friend Newton, not just the apple, but Newton's law of viscosity, so obviously there. Bernoulli's principle, if you're an engineer, you know pressure and velocity relationships. And Euler didn't really bother much about viscosity. He was looking at how flows occur if there was no viscosity. And at that time, viscosity was not really considered a thing. But then came Navier and Stokes, and they started introducing viscosity. Okay? And this is the famous Navier-Stokes equations, which resulted in modern-day developments and all that. Now, as I was preparing through the inaugural, I promised myself there won't be any equations and there won't be any references. So don't worry. So no equations here. Okay? And of course, we've got Lord Kelvin, Reynolds, and Rayleigh. Lord Kelvin is from Glasgow, so people from Glasgow would revere him. A lot of input into fluid dynamics. You have the Kelvin-Helmholtz instability, you name it. You have everything there. Reynolds number, you've got the Rayleigh plateau instability. You've got a lot of stuff, a lot of input coming from them. One of the major book writers for fluid dynamics was Horace Lamb. Okay? And he obviously wrote the treatise on hydrodynamics. And the first edition, I think he wrote about 4 editions himself. And in the 4th edition, actually, he was talking about why flows are unstable. Flows are never stable. They're always moving. They're constantly unstable. And one of the persons whom he actually approached about stability of flows was Sommerfeld, Arnold Sommerfeld. And when he was speaking to Arnold Sommerfeld, he said, no, there's actually another person. He's from Ireland. He's Orr. And in fact, both of them developed the Orr-Sommerfeld equations, which govern the stabilities of flows simultaneously but independently. And in the 4th edition, that was where he said, yeah, the Navier-Stokes equations can be reduced to Orr-Sommerfeld equations to understand the stability. Anyway, that's the impact of Orr and Sommerfeld here. And of course, there was a rest of all the other people. You've got von Karman, that's what the vortices are. You've got Taylor, G.I. Taylor. You've got Prandtl. Prandtl in Germany, he wrote one of the most defining papers in fluid dynamics, talking about boundary layers. Okay? And then Tolmine and Schlichting worked on this and developed the Tolmine-Schlichting instabilities. So basically, you've got a lot of work going on right from 17th to the 20th century. And then 21st century came. You've got Landau and Batchelor. Landau was actually arrested because he protested against Stalin. He was initially a socialist, but then he was completely disenchanted by what Stalin was doing. And he wrote that this is worse than Hitler, and he was arrested. And because he was arrested, Kapitsa and several of the Nobel laureates wrote to Stalin saying that if you don't release him, we are going to stop all our scientific work. And he was released after 1 year. But then he continued working, but then he died after an accident. So Landau also has a huge impact in terms of fluid dynamics, in terms of understanding the stability of fluid. And of course, George Batchelor of Cambridge fame as well. But if you see over here, you see mostly men. And this is a fact because in most of our textbooks, you will encounter all these people, most of these people, if not all of them. But one of them who's always missed out is Lady Zanskaya. She is the one, I would say, who gave birth to numerical fluid dynamics. She's the one who said, if you have a partial differential equation, if you have these complex equations, you can solve them numerically. Okay? And unfortunately, none of the CFD books that we actually read today, they actually point out to her. None of them, or hardly any of them. Okay? So I think there is something which we should all learn when we decolonize or degenderize the curriculum. It's not just about mentioning all of them, but actually also pointing out the right people who have advanced the modern study to a great extent. Okay, so shifting gears. So one of the things I'm going to ask you is, what language do flows speak? Okay, this is so last year. This is 10th June 2020. There was an solar eclipse, and I shot it with my lenses and all that. I shot it through my mobile phone. Yeah, so you can see this. Obviously, you see all these clouds. There's the sun. It was great. It was great to see the sun having the eclipse. But one thing what you can see is, what can you say about the flow of the clouds? There's hardly steady. It's basically, this is one of the statements from a textbook. It says laminar or organized flow is an exception rather than the rule to fluid motion. So obviously, flows are completely unsteady. What we're going to do now is we're going to look at some small experiment. Anak, do you want to come on? Okay. So just put some water. Okay. Now we'll put some oil. Okay, now you've got some job here, okay? So can you tell me what is happening to oil and water? Are they mixing?
No.
Okay. Take the spoon. Obviously, it's not mixing. You can see that they're completely separate, right? Now, what you can do is just add some fairy. Now you know what happens in our house. So, okay. So this is, initially it was completely stable. Now can you mix it? And take it off? Can you see if it separates out? Is it separating off?
Yeah.
Is it? Is it separating off very clearly? Or is it pretty muddy?
Not separating off clearly.
It's not separating off, right? So basically what has happened is this has disturbed the interface. This has disturbed that interface, and then it's actually encapsulating oil and water together. So you've got something called as emulsion. Please don't drink it, but this is what is an emulsion. Yeah. Now what we're going to do, another thing is, can you just put some? What is your favorite color? You mentioned that. Is it red? Just put some dye. Put some dye. It's okay. Okay. Okay, fine. Now we'll just put some oil as well. Let me just do that for you. We just put a lot of oil. Okay. If we were doing this at home, my wife would say, just go out. Because so much of oil is being wasted. Okay, right. And then we'll see if we can develop a lava lamp. Let's see. Probably this one is better. Can you just put some? Just put all of them. So you had a very stable interface, and let's see what happens now. Ooh, what's happening?
Some of the oil is coming to the top.
Is it oil or water? What is this? This is water, right?
Yeah.
Yeah. So you got these bubbling going on, right? Is anything happening? Yeah, it's happening. Okay. Let's put some more. Let's give it some time. Yeah, there's a lot of activity happening. What's happening? You can see a lava lamp.
Yeah.
So you can see that that water is actually being pushed up there, and then at some point you will see all the water coming back. So you have destabilized this interface, and then you're actually creating. It's an unstable. You've got a heavy fluid sitting on top of a lighter fluid, which is a weird thing. So therefore, it just will sink down again. So this will happen. So this is one of the lava lamps. So this shows something called as the Rayleigh-Taylor instability. So you got this thick thing, which is a higher density fluid, which is actually settling down slowly. Actually, you can see these mushrooms which are just coming down. So thanks, Anak. Thank you. You can just go. Yeah. So basically one of the things that we can see is flows are never stable. So they're always unstable. And one of the things as engineers is we want to really. This is basically it's a Sanskrit poem translated into English by one of India's most leading fluid dynamicists who recently expired, who recently passed away. He's Roddam Narasimha. So he says it takes both of its wings for a bird to fly about in the sky. So it takes both knowing and doing for humans to perfect themselves. This is exactly what engineers do. So basically we know, we do, then we relearn again, and then we perfect ourselves, or we try to perfect ourselves. So basically that's a very important thing for us, and that's a very important thing that engineers do. And obviously one of the things that you can see is all the flows speak the language of instabilities. So everything that happens in flows, what you can see is because of the instabilities within the flows. Okay? So what happens within my research group? Within my research group, So obviously we tackle all kinds of issues. We tackle whether it's related to energy, healthcare, or environment. We solve it using theory and simulation, so we can do both. We also do some experiments, but in my group it's a bit different. Usually people do experiments first and then go over there. I read the book from the back side, you can imagine. So I first do the theory and simulations, and then if I find something interesting, and thankfully most of my students have found a lot of things interesting, and we check through the experiments if it's correct or not. Okay, so basically we first do this and then we go to experiment. And once we are satisfied that yes, we are doing, and in fact experiments can tell us more in terms of whether our theory is working or not, but at the same time they confirm whatever simulations that we do and whatever new phenomena that we have seen. And obviously all of this goes into technology transfer and dissemination. Now when it comes to usually for engineers, for technology transfer, we collaborate with companies and we write papers for dissemination and all this. But what about, this is just an idea, what about for people who are visually impaired? How do you communicate your science to people who are visually impaired? I mean, obviously people do that. I mean, for example, astronomers, they have developed, they have used sound to actually communicate their science to engineers, to visually impaired. So one of the ideas here is basically to look at sound. Okay, so here I'm going to be reading out. So this is basically my cousin. She's a part of a band in Chicago, and what they have developed for me is I have supplied some videos, and she actually put out a sound representation for that. So in this case, this is about laminar and turbulent flow. So you can see smoke's going like that. It's almost streamlined. So, and what she has named it as is, she has named it as Zug und Ruhe, which is in German, migratory restlessness in birds. And I'm just reading out what she has written here. So each layer of smoke is represented by an instrument. The drums and the bass are at the bottom. The drums represent the nature of the domain. The loop section is where the eddies form due to some disturbance, which is the instability. And the beginning of instability and unevenness is signaled by the drums. Okay? So let's just play and see. So yeah, so this is just an idea about superimposing or creating a music specifically to a certain flow, okay? And obviously she did ask me about what do you want and what I wanted to convey and things like that. And therefore she developed this. Just to take another step, so I'm just going to come back to this again. So what I'm going to do is I'm going to just show what happens within my research group in certain areas. And in some of those areas, I'll actually play back the sound. You can see the influence of sound there. Okay, so this is basically the work on brains and strokes. So Stephen Blowers is right here. So he graduated from his PhD in 2017. This is alongside the College of Medicine. So you got Ian, Peter, and Joanna, and Mike, Bridget. And of course, Ian Bethune was from the EPCC. So there's a lot of input in my work from the EPCC angle as well. And for those who are online, they can scan this and you can see the code. So what does he do? So Stephen, we were looking at problems of brain trauma. So any kind of an accident can result in inflammation. And inflammation in the brain, one idea possibly is to use hypothermia to help alleviate some symptoms. And it has seemed to help, at least in the short term. Okay? So what Stephen and actually what Ian and Peter asked me is, we want to understand how exactly this happens. What is the temperature map in a brain? Okay, so what did Stephen do is he actually browsed through, well, he obtained data. Yeah, he obtained data. So he had these vessel data, and then what he did was he grew these artificial vessels using literature, because obviously when you do MRI or when you do all these methods, you can't really scan every single vessel. So beyond a few millimeters, especially micron-sized vessels, you cannot scan them. So what he had to do was basically look at weighting factors to make sure that the vessels grow in appropriate areas. So this is basically like cabbage, and this is the brain blood vessel network. Okay, and then he put this into the brain tissue. Okay, so this is obviously numerically done. He puts this into the brain tissue, and then he actually solves flow. He solves for flow. So you can see that there's flow. He can track the motion of blood. He can also track what the perfusion is, how does blood get into the tissues, and all that. Okay, and at the same time, he's also able to measure temperature. He's also able to calculate temperature. Okay, Luke is the current student, and what we have done specifically is use Stephen's code to extend it to understand strokes. So for example, if there is a stroke, if there is a major stroke, usually if it's a major stroke, it's a catastrophe. So we wanted to understand what happens when you have a major stroke and how does it impact. So if you see, when the stroke is a major stroke, you can see a large number of blood vessels being red. You can see that there's a huge amount of brain which is impacted. Okay, this is perfusion. But at the same time, we can get temperature data as well. Okay, we can measure how the temperature is varying. And as and when your stroke is minimized, so for example, if you go from the 0th generation, that is your clot is at the 0th generation, so you've got a major stroke. But then as you progress up higher in the generation tree, your stroke is minor and minor. And as you get to minor strokes, we also check about what is the temperature influence, how does whether hypothermia can help or not, and so on. So this is in collaboration with, as I mentioned, College of Medicine and EPCC. Okay. Another aspect of work is about backbone and breathing. So this was a very interesting project. It's still going on. So these are very early stages, I would say. So this is alongside Enrique Garrido from the Sick Kids Hospital and Jamie Farrell, who graduated with a PhD on that. So this is about scoliosis, actually. So if you have a straight spine, everything is fine. But then scoliosis happens at birth, usually. Usually at birth, and then it can progressively get exacerbated. So you can see the angle of this bend over here. It can get really severe. And what happens here is you can see that, why does it jump? Yeah. So what you can see is you can see that you've got this you've got the backbone here, and you've got the lungs, and they're being compressed actually. So if you see this is how it is. Oh, if you see this, you can see that it's actually compressing one of the major airways. And if you do a CFD study on it, so what Jamie did was not really much of CFD. He was looking mainly at the morphological data. So he analyzed a huge data set of patients to understand what type of scoliosis, what levels of scoliosis can occur, and things like that. So the next step is that we look at the fluid dynamics in the airways. And you can see that this is a sample calculation, and you can see a lot of stress happening at the upper airway, indicating, and basically these tools are very useful especially for surgeons to check when is a highly interventional surgery needed. Because with scoliosis, as you know, the surgery can be really interventional. It can be really invasive. So this is still going on. So this is so Jamie has graduated, and so there is an open. So there is a PhD post open. So this can be considered as an advert as well. So if you know of someone who wants to do a PhD, let me know. Thanks. And of course, another aspect of that was about healthcare. Another aspect of the work that we do is about environment and carbon capture. So this is work done by Patrick Schmidt, Gianluca Laval. They were PhDs and PDRAs in 2016, and also Paul Tate. Paul Tate was mainly the experimentalist. Patrick was the simulator, but he also did experiments in the company. So Mark Worley is from Sulzer. And this is what, I'm going to show you a model soon, and this is along with Matthew and Len from UC Dublin. So if you look at, in terms of carbon capture, obviously you've seen the Grangemouth refinery, you've got these huge columns. These columns are refining, they're distilling stuff, or they're absorbing stuff. And what you have inside them are things like this. So these are packings inside a column. Okay, and this is from Sulzer. So what happens is, you've got this column, you've got gas which is going up, and liquid which is actually raining down. And as it does, as it rains down, it actually interacts with the gas phase, and there's a lot of heat and mass transfer happening. Okay, so the idea was to understand this a bit more clearly, because there are so many empirical relationships there, but we know that they don't really work. So we wanted to understand how we can do this better. So if you look at this, so this is what it is. You've got packings inside it, and these packings, the way it happens is you've got gas going up and liquid actually raining down as a fine film. Okay, so what Patrick did was actually look at this in a complete numerical sense. So you can see this. So this is a liquid film which is actually flowing down, and there is a gas phase which is going up, and you can see that this is the industrial range of operation. So this is a very high flow rates, and you've got liquid which is raining down, but the waves are being transmitted upwards. So the more waves you have, the more mass transfer actually you can have, because there is an availability of surface area. So basically Patrick was looking at the regions of operation for Mark Worley's packings as well, and together with Gianluca. And it was Paul Tate who did the experiment. So this is in 3 dimensions. This is what Gianluca's simulation showed. This is how the complex interface looks like. So as you really increase your gas flow rate, your interface can tear up. And this is where usually industrial operations occur, because that's when you have a lot of interfacial area. You can maximize your efficiency, your columns, energy efficiency for your columns. So this is one of the projects about carbon capture related to the environment. The other project which I'm going to talk about briefly is about tumbling chaotic solids. So you can see this work was basically by Pei Shui and Eric Esman. They graduated, Pei Shui graduated in 2015, and Eric in 2019. In fact, Pei Shui, I had sent him to Stefan Zaleski's lab in Paris to understand more about the code which they're developing, and then he redeveloped his own code to actually simulate these flows. I'm going to talk to you more about that. And this is in collaboration with David and Mark Sawyer from EPCC as well, and Rama Govindarajan from TIFR in Bangalore. So if you look at this, if you look at the main problem, the problem is that you've got solid fluid flows in any company. If you are in a chemical company, pharmaceuticals, you name it, you will deal with solids. And these solids are mixed with liquids all the time, and they flow together. But as they flow together, there is a tendency that they can clump together, so that they can actually jam your equipment. And this predominantly can happen in subsea pipelines. So in subsea pipelines, you've got obviously subsea is subsea. You've got the temperature of 4 degrees Celsius approximately, and extremely high pressures. And at that pressures, you can form ice within the flow, within the gas phase. And actually, these ice particles can grow to become larger objects, and they actually can clog the pipe. And these are called as hydrates. So these hydrates, what companies do is actually pump in a lot of hydrate inhibitors. So several thousands of dollars goes into that. And then that increases the load on the pipe. But at the same time, they want to make sure that you can't prevent the formation of hydrates, but you can actually let them flow. So if you want to make it flow, you want to make sure that it doesn't really clog up again. Okay? So what Pei was looking at is how can solids actually flow in liquids. Okay? So these are not particles, these are bigger solids. Okay? So if you look at this, you have 2 solids. You've got 2 solids. This is Pei's code. If they're at a certain distance apart, they actually fly away from each other. So they are actually hydrodynamically repelling each other. But at a critical distance, they actually tumble together. So that's what you want to avoid. This can form a clump and an agglomerate. Okay? So this is what you want to avoid. So what we were looking at is basically what are the conditions that lead to this. Okay? The other thing what he's also looked at is looking at how these particles, how these solids behave close to the wall. Some of them can get lifted as they tumble, but if you can imagine you have a clump like this, it may actually settle down faster. Okay, it may settle down faster because gravity will win. Okay, so one of the main things that you want to see is how the motion of these particles is. So what Eric did is, hold on. Yeah, what Eric did is basically looking at these particles, how these move. So some of them can move in a very boring fashion, just tumbling around like this. But in some cases, they move very chaotically. Okay. Now you can imagine in your flows, if you have a lot of other particles, they can either demonstrate a chaotic motion or they can demonstrate a periodic motion. So obviously, at this moment in time, we don't know which one is good because we are still studying that. Okay. We don't know which one is good, but hopefully, by the help of Andrew, who's actually putting more particles in, we'll be able to tell you what exactly is the answer. Okay, so this is about chaotic solids, and you can also download this code from this link here. Now, this is an important slide, I would say. The reason this is important slide is because it's a tribute to my supervisors here. So Jeff and Omar and Peter Spelt. Jeff and Peter actually passed away recently. In fact, their families are listening online. So thank you so much for coming. And in fact, under the aegis of something called as a transient multiphase flow program, we had investigated several problems alongside Omar and Chris and Lennon and everyone else. Okay, so some of the things that we looked at was basically, obviously, in any kind of a pipeline. This could be in any type of a two-phase flow system, any kind of multi-phase flow system, not just oil and gas pipelines. But transient TMF program was mainly for oil and gas. So this is what happens in your pipeline. So you can have either a central gas core which is running, and you've got a liquid film on the sides. This is an annular flow, and you can see the waves. So this is on a transparent, this is on a Perspex tube, I think, and basically you can see the waves running around. Okay? In some cases, if you change your flow rates, you would actually see these churn flow patterns, which is a highly complex pattern. And each of these patterns poses a challenge for the industry because they have a massively different pressure drops. Okay? So you don't really know what your pressure requirements is. Okay? And in some cases, you can develop something like a tsunami. This causes a lot of throughput problems for oil and gas companies. So we wanted to know what exactly leads to these cases. So what we did was we obviously developed a numerical solver alongside EPCC. But then this was original solver by Peter Spelt and Omar. And Jeff, though being an experimentalist, he was a fervent advocate of brand new codes and especially powerful ones. So here is an example by Lennon, actually. So you can see that this is an interface. A wave starts off as a very small wave. So these are infinitesimally small, but you can see how fast they grow. So you can see that as they grow, you can see a kind of a wave which is traveling down. But as it travels down, it actually develops a three-dimensional feature. You've got an S-shaped instability kicking off. This is a 3D instability. And as it becomes bigger and bigger, it actually grows into tongues. And obviously, this is not exactly slug flow, but this is a wavy stratified flow. But you can imagine that if your pipe is half full, you can easily get into this. Okay, you can easily get into this, and that can cause severe issues. The other thing that we dealt with is also another problem. This is with Unilever, actually, and FMCG companies. So what FMCG companies do is when they manufacture a toothpaste, they use the same plant to manufacture another brand of toothpaste. So essentially, it's a batch operation. So between each batches, they have to clean the plant vigorously. So there is a lot of energy, there's a lot of water, then there's a lot of chemicals used to make sure that it is FDA grade clean. Okay? But then if you have something like a toothpaste, it's a very stubborn thing. It will not clean up well at all. So it will just be actually pushing through. It'll just be sitting there. So one of the things that we did is basically look at chemical cleaning as well. So you can see the pushing of this and then completely clearing off this gunk from here. So this is with Kirti Sahu as well as Omar and Hang. Okay, so this is a very important slide as well. So this is about, and you can see things coming up now. So this is about evaporating drops in films. So you've got, so this, I would say, blame everything on Pedro, because he's the one who started the whole thing. Well, he was my first PhD student. And we worked on evaporating drops. So I'm going to show you, so this is basically a microprocessor. So everyone wants to have a faster microprocessor nowadays. And you want to cool them, because obviously if you don't cool them, you will burn it out. So if you want to cool them, you need to have proper cooling. So if you look at your laptops nowadays, you got these fans, but we know that 40% of air does not do anything. Okay? So if you want to create a mini fridge, that would probably be most efficient. So here is an experiment by my colleague Khalil. You've got a methanol drop as it evaporates. As it evaporates, you can see that it's generating these kinds of waves, and we wanted to study what these waves are. Because unless and until you know this, we can't really design an efficient coolant. Pedro came along, and then he said, no, I want to simulate the whole thing. So as he simulated, this is the first simulation of a three-dimensional evaporating droplet. He could see azimuthal currents established here. This was one of the first results that ever came off. I mean, this was one of the newest, newest knowledge that came out from this study. And he also measured it. I'll just play this again. He's also measured it using experiments, and you can see even if you have a complex shaped droplet, you can see these kinds of patterns over here. Okay, these are temperature patterns. Okay, so this was very good. But Pedro, being Pedro, he did not rest. What he did was he then added another component. He said, this is all pure fluids. No one uses a pure fluid as a coolant. I want to use industrial grade. I want to add something volatile to it. So he added ethanol. And if you remember about the music, so I'm going to just tell you what exactly it is. I'll let it play and then I'll tell you. So my cousin named it as Flutter, and this one is based on two fluids. Obviously, there were two fluids evaporating at the same time. And what you saw is those clouds. So the brighter one was actually ethanol, and the other one was basically water. Okay? So you could see that there was segregation. So initially, they appeared as the same fluid, but then they segregated. Yeah? So this one is based on two different fluids evaporating together. There are three pairs of two instruments which represent separate fluids, and they start influencing each other. Okay? So that was what Pedro did. Then Adam came along. Adam is sitting here. And what he said is, no, Pedro did just a kind of a confined droplet. He had these weird shapes and all that. I want to let the droplet be as natural as possible. So he just put a droplet on a very smooth substrate. And again, this is, Adam, you'll recognize this video, but it now has music. So before it starts playing, I'm going to tell you, look for the octopus here. You can see this one. So you can see, so what she writes is, two fluids that look like one, together in a single drop, display their individual nature when subject to transition through rapid evaporation. One of the fluids takes shape of sharp tentacles that after evaporation leaves behind a ghost of another fluid to trace. The sounds chosen to represent two fluids are sharp and rounded to follow the liquid's visuality, reminiscent of the Bouba-Kiki effect. Okay? So this is one way of probably representing Adam's videos. Adam would be shocked to see this, but anyway. Then Yu Hong came along and she said, no, I want to see that my substrate is not rigid. It's going to be a flexible substrate. And as she evaporates stuff, you can see that the whole thing folds off. Okay? The next person who came along was Hongyu, I think. Hongyu said, no surface is uniform. You'll have some heterogeneity there. Can we not exploit the heterogeneity to actually let the droplet move. So this particular side has a different surface structure than the other one, and you can see that the droplet moves by this. So this is a good opportunity for self-cleaning substrates and things like that. Robson actually looked at fluids which are actually evaporating, and as it evaporates, they actually generate patterns. And you can see, as the simulation evolves, you can see the patterns generating. Give it a few minutes. If you give it a few seconds, it'll just finish. It's developing. You can see that there are waves developing, and then you can see these patterns that are generated. So this is actually a one-dimensional code, but you can see these patterns, and these remain like that. So you can imagine that you can have these patterns that are deposited. So this was alongside George and Omar and Jungo and everyone. Katie and Zhenying Wang actually looked at desiccant droplets. So you got this 2 desiccant droplets containing lithium bromide. So obviously one is actually pulling off moisture from the other. So one guy keeps becoming large and the other guy gets smaller. Joey Kilbride, from student of Dave Fairhurst, is looking at the populations of these droplets, Dave Fairhurst and Fauzier. So that is also work ongoing alongside Stephen Wilson. So this is about evaporating drops. The next thing I want to do is basically talk about boiling. So one of the things that boiling is common, very common. You can see these are experiments by Zhongwei. So you can see these bubbles which are formed. You've got these multiple bubbles, and you've got these single bubbles which are just rising away. What Gerda and Mutsa have done is basically look at the simulations, but alongside Alessio and Ed Smith, we are looking at the nucleation events as well. So if you look at this is a molecular surface and containing a liquid, and then you can see nucleation events happening at some points here. You can see that. And as many of these happen, the entire thing gets lifted and you go to film boiling. And this is a molecular dynamics simulation. Okay? So this is at the molecular level. Gerda and Mutsa are looking at a macro scale. So I'm going to show you this. So basically, you've got these drops. You've got these bubbles which are rising in the plume of liquid. Okay. Now we have one more demonstration to make. Anak, do you want to come in? Let's see if it works. But let's see. You remember this?
Yeah.
Yeah. And can you just we have taken risk assessment and all that. So still there? Oh, something is happening. So what's happening is your water gets sucked in, it boils off, and then you generate a steamboat. Yeah, so there's actually flow boiling happening there. So the next bit was basically about flow boiling. I wanted to go. Yeah, we do this all the time at home. Oh, that's going well. So this is a gift to me by one of my colleagues, Yas Takata. What's happening there? Oh, Great. So this is what is flow boiling about. So you got these. Anak, you can go and sit down. Yeah. So you can see that you got these bubbles which are actually moving about, and these are Taylor bubbles. This was actually simulated by a number of our South African colleagues, Joshua Mayer, Ken, and Lewis, Jared, Marius, and everyone. So we are also looking at jet boiling actually. The way if you want to cool stuff, one thing you can do is you can actually rain down jets. And as jets develop, you can actually see cooling that is happening. So this is obviously alongside several of my colleagues. You can see Tim here, of course, along with Anthony Walton and John Terry, Tim is also supervising GRS. So there's a lot of input that is going on in terms of boiling as well. Now, I'm going to be talking about another stuff, which is just the last slide actually, about shouting at bubbles. So one thing that you can look at is, I think this will not stop. I'll just switch it off. Yeah. So one thing that you can look at is if you have any bubble, what do you want to do? What can you do what is the impact of the bubble on sound? So basically, this is Davide's experiment. Davide is sitting here. So he's put a transducer, and this is just a bath of water, and you can see these small bubbles creating these streamers, and you can hear the noise as well. Now what he did was he also went to Glasgow to Paul Prentice's lab and actually did a very detailed experiment. So using Paul's excellent visualization facilities actually. So this is the sound, which is actually the natural sound of the bubble as it actually periodically vibrates. So previously we looked at superimposed sound, but this is basically taking the Fourier transform and everything and converting that into sound waves. So basically, thanks to James for helping us do this, because it was through his input that we could actually get the background sound. So this project is together with Stephen Shaw, who's an expert in terms of shocks and in terms of bubble dynamics, as well as Rama Govindarajan from TIFR Bangalore. And if you increase the amplitude of the sound, you can actually see these weird perturbations all over the place. So this is Davide's project. So hopefully, in all of these things, I'm able to show different types of instabilities that we look at in different types of flows, actually. So just to briefly sum up, obviously I'm inspired by everyone. So what I've done is I've written a small haiku. Haiku is a simple poem in Japanese, but in English, I've used the principle of 3-5-3. So family, friends, and teachers shape, inspire, develop, support, strengthen, and meaning to life. So these are my parents, my in-laws, of course my wife. You've seen her. And you can see that she's actually looking at me in a certain way because I've done something stupid. And these are my in-laws as well here. And of course, my uncles who have been inspiring me a lot. So my uncle here, G. Prasad, he's a chief metallurgist in BARC. So he was the one who actually inspired me to study chemistry more and things like that. My uncle, S.M. Rao, he was the head of the isotope division. So here is my son playing with them. Of course, they asked me to study more so. And one of the important persons I must highlight is my uncle S.S.P. Rao, who was the head of computer engineering department in IIT Bombay, and it was him who taught me programming. So that was when I was probably in A levels or just before A levels. So all thanks to them. Of course, a huge family I have. I'm a single person. I don't have any siblings, but I've got a huge number of cousins all over the place. So thank you to all of them for inspiring me constantly. You can see my aunt. And this is Satya. She's the one who was superimposing music. So she's the one who is the composer. Of course, my teachers, what can I say? Omar and Jeff, they know everything about me. Omar especially, he's like my academic dad. So he knows everything about me, and he's been telling me what to do, what not to do, and now he's a fantastic collaborator as well. Peter here. Peter, sadly, he passed away last year. This was the time when we met in Dublin last year, in 2019, actually. You can see Rama playing with my kid. Here, when I showed this picture to my wife in 2015, she said, both you and Khalil look like smugglers kidnapping this guy. I said, no, it's just too cruel, no. So this is a much more decent picture of myself with Khalil. You've got Yas Takata here. You've got this is Matar alumni. So obviously all students of Matar, Omar Matar, meeting up and doing fantastic work. So you've got Jungo, you've got John Christie, you've got Martin Shanahan, and everyone here. Thanks to the entire School of Engineering who has been so inspiring. And I should mention Professor Bill Eason, who was my predecessor. I think he was the professor of fluid dynamics and essentially I have inherited the post from him. And a big thanks to the engineering grad school. Of course, the next generation. See, Davide is showing off here. He's just playing a Chinese instrument. So the next generation, our students and children inspire us, will carry the flame. So all of these students, every one of them, we have met, we have done a lot of stuff, but we learned a lot together as well. So thank you so much, all of you. The other thing, of course, is my collaborators. So I have collaborated far and wide, and this will continue on. And this is important because if you want to have inclusive science and engineering, you have to have global collaborations and to solve global challenges. When we say global, it has to be global. Okay? And in fact, fluid dynamics is a powerhouse in UK. Okay? If you've seen this report, which has been recently published by Kath Knox and other colleagues in Leeds, you will see how much of economic impact fluid dynamics has in the UK. Okay? But we can do a lot more. We can actually be very, very creative. We can actually think more creatively about our centers for doctoral training, for example. In fact, we now have national postdoctoral fellowships which are coming up for fluid dynamics. But we can do even more. We are doing much more. I was fortunate to have the opportunity to be in the tomorrow's engineering challenges. And in fact, tomorrow is the next, I think the last session is tomorrow as well with the EPSRC. So we are thinking about what is the thing for the next 15, 20 years, and it's fascinating discussions all through. And fluids and engineering plays a huge role in everything. Okay? For some reason it stopped. Okay. So acknowledgements. Thank you for all of my ThermoSmart colleagues, 21 partners. And big thank you to these people actually, Hazel, Kate, Nuria, Miriam, who's actually currently dealing the project with me, and also Kasia Lyson from EC. And of course, thank you everyone, including JSPS, EAPSRC, and all the funders. Thank you so much.
My name is Professor Crahura O'Brody. I'm the Head of School of Engineering, and it's my great pleasure and honour to propose the vote of thanks for Prash's excellent lecture. And I'd just like to say that for much of the presentation, Prash wasn't visible to his legion of followers and family online, so we've made him stand in front of the camera over here. And just to reassure people that the fantastic experiments which were done during the lecture will be available on the recording afterwards, which will be available to everybody online. So I have to say that, first of all, it's a fantastic pleasure to be back to doing inaugural lectures. This is our first one, which was done in a hybrid sense, so you'll have to forgive us for if there were a few little technical hitches along the way. But what a wide-ranging and very interesting talk. And as well as being interesting, it was also very cultured. We had music set to fluid mechanics experiments. We had haikus composed by our resident haiku master in the school. So we certainly learned a lot of things about Prash tonight. And speaking as more of a solid mechanics and a materials person, I think Prash made a fairly convincing argument for fluids being pretty fundamental to human life. And of course, if you think about it, most of the creation myths of humankind, and indeed the science, suggest that human life began in water at the very start. And of course, human conception is greatly aided by fluid mechanics. And all of us were protected by fluids and indeed nourished by fluids for the 9 months before we were born. So perhaps I have to concede to fluid mechanics on that side. You know, what a wide-ranging presentation. We had the history of fluid mechanics and the understanding of instabilities. We had interesting biomedical applications. We had all kinds of industrial applications, carbon capture, tumbling solids in oil pipelines. We had waves and slugs in oil transport. We had manufacturing problems with toothpaste. We had evaporating drops and films, boiling and indeed dancing bubbles. So very, very wide-ranging, and I would say a great example of how fundamental understanding of physical processes, fundamental modelling of physical processes can be used and applied to important industrial and other problems. And that was what struck me about the talk. Prash is a fantastic researcher. He's very, very widely internationally recognised, and I think what struck me about his talk was the wide range of collaborators. I think he must have had at least 100 collaborators listed in his presentations, and he very generously acknowledged all of their contributions to his work. And I think a lot of them are online. He's an excellent teacher. He's much loved by our students, and I think you can appreciate why after seeing his lecture. The enthusiasm just oozes from him, and this really aids when, I'm sure, communicating fairly complex equations, which he spared us any equations tonight, I have to say. I was a little bit disappointed. I would have liked one. Okay. I was quite surprised that he's quite the experimentalist, along with his son Anak. Very, very interesting, and those of you that didn't see it online, you'll see it in the recording. Very, very interesting. And of course, he's also the director of our postgraduate school, and has a very, very key role to play in the education of over 500 PhD students currently in our School of Engineering. And I think quite justifiably, I would say, one of our most popular staff members, both among his colleagues and in the school, but also with the students at both taught students and research students. So it's my great pleasure to propose a vote of thanks and a round of applause for what I think was a fantastic, inspirational and brave inaugural lecture.
Thank you. Thank you.
So we're going to attempt some hybrid questioning of the new professor, and
I can allow the microphone, but the person on the other end will have to unmute themselves.
okay. I think what we'll do is to keep things simple. Can we ask people to put some questions in the text box, Eddie? Okay. So if any of the people online would like to put some questions in the text box for Prash, we'll relay them and have him answer them. But perhaps some of the people here in the audience would like to kick it off with a question. Okay. One of the things I'd like to ask Prash, you were a bit unassuming in your presentation. Could you say a little bit about you've had a big impact through your open source flow solvers? Could you say a bit about that? Maybe go back over there with
Sure.
people online can see it.
So I think so. Actually, I should have.
A bit about the solvers and the impact they've had.
Sure. So so one of the things that when I was interviewed for University of Edinburgh position, I was asked where do I see myself in about 5 years' time or whatever it was. And one of the things I did mention was that we can develop bespoke solvers and make it available to a wider public. And one of the questions was how. So the important thing is whatever solvers we generate for flow, we can actually put them online. It's freely available to anyone. So that's what open source means. And this was thanks to colleagues from EPCC here. And one of the impacts it has had is especially TPLS, the two-phase level set solver. It has been downloaded about 2,000, maybe 1,800 times from over 56 countries or whatever it is. So, I mean, that's the impact. Obviously, one of the drawbacks one would say is we don't know what people are doing with it. But at the same time, I'm happy that at least it's being used. The other thing which is good is even industries, they have looked into this solver. Well, how they have used it, it's up to them. Because obviously that comes into this proprietary thing. So the solver itself is free, but whatever people want to do can become proprietary. So yeah.
Fantastic. Now we have a question from one of your colleagues online. If you had to pick your favorite or perhaps top 2 projects, what would they be?
Oh. I think we can do a lot. I think all of my projects are my pet projects. That's not permitted? Okay. But there are some really interesting problems that we all can solve. For example, especially
You're not answering the question. He's avoiding the question. I'm going to pull rank and insist that you tell us what your top favorite project and maybe second favorite.
So, I'll say one of my top favorite projects has been ThermoSmart.
Okay. Tell us a bit more about it.
So it takes care of everything that is to do with phase change. Okay. So that includes a number of my colleagues there. And of course, the next project which we are actually looking into more carefully is the boiling project, along with Omar and others. So they are currently my focus at the moment. But then there are really interesting problems that we can do, especially in terms of critical care. Kenny is here. So in terms of critical care, especially accessible critical care in extremely remote environments, I think we can do a lot more to make sure that critical care is affordable.
You can see why the students give out about the feedback that they get from their professors at the University of Edinburgh. So a little bit of evasion there, Prashant.
Yes.
I'll let you off with it. Tell me this, another question. What would you say to the younger kids to interest them in this line of study? Because let's be honest, it's quite mathematically rigorous.
Yes.
Quite mathematically different and difficult. So how do we persuade younger kids to study maths and science so that they've got the tools to become engineers?
Very good question.
Perhaps get into fluid mechanics.
Yeah, very good question. So one thing I keep telling all the kids who approach me for maths, and I'll tell it for my son as well, is maths is another language. It's simply a language. You have an equal to sign, which means that both sides are balanced. Okay, maths is a language, and if you read that as a language, it's beautiful. It's absolutely beautiful. You can actually make maths work for you, to make maths let you understand the phenomena you're looking at. So essentially, rather than writing in words, we can write it in maths. So maths is a beautiful language, and I should give credit to my mum, actually, who inspired me to really look into maths in that way. Okay, not as some kind of a separate thing and alien stuff. No, it is intricately related to our lives. It is intricately related to chemistry, physics, biology, you name it. And it's I think it was Galileo who said that it's the language of God, or whatever it's called. So yeah, so it is.
And clearly having a strong scientific family such as yourself is also an aid.
Yes.
Is also an aid towards developing an interest. And it struck me in your talk tonight that it was very interesting to see cousins providing the music, your son providing the experiments, your uncles providing inspiration, and now your mother is making you study.
Yeah.
So it obviously takes a lot of people to produce a great researcher.
Yeah.
Now we have a question up here. James has a question.
The question was, because maths is such a beautiful language, if you were to get one of those T-shirts with a maths equation, just one, because Cahill wanted one, what would that formula be, and why? And then the second question is, would you wear that T-shirt?
I would definitely wear the T-shirt, and it would be simply F is equal to ma, Newton's second law, because that ultimately leads to equations of momentum and force balance. That's it. That's my favorite equation.
And would you wear the T-shirt?
Yes, I would.
Would you get us one as well?
Yes, please.
Very good. Any other questions? You see if there may be one more online. Anybody asking questions? No. Okay. So I think Prash has entertained us, has stimulated our interest, has presented a fantastic description of all the work that he does. And I think from an engineering point of view has presented an image of a fantastic person that can bring fundamental understanding of engineering, fluid mechanics, etc., and bring it to life, inspire other people, and apply it to real world problems. So let's give Prash a hand, and thanks to everybody who's attended online. And just to remind you that the recording will be available in a while. I don't know how many days, but it will be available, and you'll be able to see all of the action that you missed. So thanks very much again, Prash.
Thank you. Thank you, everyone.